Hello, we're Inbal and Nicole, and today we'll be presenting our project on lung cancer detection using deep learning. The goal of this project is to classify lung cancer images into different categories based on their characteristics and severity. Lung cancer is one of the leading causes of death worldwide, and early detection can significantly improve patient outcomes. With this in mind, we utilize advanced deep learning algorithms to improve classification accuracy and assist in early diagnosis. During this presentation, we will guide you through our notebook and explain our approach, including the tools, methods, and results of our project.
We start with importing the necessary libraries for tasks like data manipulation, visualization, machine learning, and deep learning. Next, we download the lung cancer datasets from Kaggle using Kaggle Hub and move it to the designed folder in Google Drive. The dataset structure is printed showing root directories and subdirectories. We define the input shape for images as 128 on 128 on 3 and set the number of classes to 3, normal, benign, and malignant. Finally, the code iterates through image categories, checking their sizes and storing the count of specific dimensions in the size data dictionary.
Here, we construct the path for each category in the lung cancer dataset and iterate through the files in each category directory. We attempt to load the first image from each category using OpenCV in Grayscale Mode 0, displaying it using Matplotlib. First, we show 3 images, one for each category in the dataset. Then we apply the following. We resize, apply Gaussian blur, and display 3 versions of images from each category. Then we create a 3-column layout for each category, showing the original image, the resized image, and the blurred image. Additionally, we adjust the size to 256 on 256 pixels and apply a Gaussian blur with the kernel size of 5 and 5. The resizing is done using CV2, and the blur is applied with CV2 Gaussian blur.
This code processes the lung cancer datasets by loading the resigning images to 256 on 256 pixels, while assigning each image a label based on its category, normal, benign, or malignant. The images and their labels are shuffled and split into features X and labels Y. The images are normalized by scaling pixel values to the range from 0 to 1 and reshape the match the required input from format for neural networks. The class distribution in Y is printed, showing the number of samples in each category, and both X and Y are converted into NumPy arrays for model training. This code splits the datasets into training and validation sets using train test split, with 822 samples in the training set and 275 samples in the validation set. It ensures that the class distribution Y is preserved across both sets using the certify equal Y parameter. The printed output confirms the number of samples in each set and shows the shape of the images, 256 on 256 on 1.
This code prints the class distribution of the training Y-train and the validation Y-valid sets before applying smooth, showing imbalances with more samples in some classes than others. It then reshapes the training images in X-train from a 4-dimensional array to a 2-dimensional array of shape, and by flattening each image into 1-dimensional vector, which is necessary for some machine learning algorithms we use later on. The reshaped X-train is then ready for the smooth technique to address the class imbalance by oversampling the minority class. In this cell, we apply smooth, which is synthetic minority oversampling technique, to balance the class distribution in the training set. Before applying smooth, the training set has different amounts of samples for each class, benign, malignant, and normal. After smooth, all 3 classes have 420 samples each, which helps address the class imbalance. Then, both the original and oversampled training data, X-train and X-train sampled, are reshaped back into a four-dimensional format to match the expected input for deep learning models. Finally, it prints the new shapes, showing that the oversampled data now has 1,260 samples.
In this section, we construct and train a custom convolutional neural network, CNN, designed from scratch for classifying land CT scan images into three categories we mentioned before. The model architecture includes three convolutional layers with increasing filter sizes, each followed by max pooling layers, to reduce spatial dimensions while retraining essential features. A fully connected dense layer with 512 neurons processes the flattened output from the convolutional layers before passing it to a final softmax layer for classification. The model was complete using the Adam optimizer with a learning rate of 0.0001 and trained for 10 epochs on the pre-processed dataset.
Next, we visualize the trained CNN model's filters and evaluate its performance. By plotting the learned filters from convolutional layers, we gain insight into the patterns the model has captured during training. The visualization reveals how the network detects features like edges, textures, and shapes, which are crucial for distinguishing between benign, malignant, and normal cases in our dataset. Next, we'll look at the confusion matrix and the graphs, which evaluate the model's performance. The training and validation accuracy and loss curves highlight the model's stability and generalization with consistent trends across epochs. During training, the model achieved impressive results, with validation accuracy reaching up to 99.27%. These results suggest that the custom CNN is effective for these classification tasks, but further improvements could still be explored using more advanced techniques that we will show you later.
Now we enhance the training process of our CNN model by introducing an early stopping mechanism. Early stopping monitors the validation loss during training and halts the process if no improvement is observed for a specific number of epochs. In our case, it's set to 3. This prevents overfitting and ensures that the model retrains the best weights from the epoch with the lowest validation loss. Using this approach, the accuracy and loss plots further validate the effectiveness of early stopping, as the validation curves align closely with the training curves, indicating strong generalization to unseen data. This is important to note that the visualization spans only a limited number of training epochs, reflecting the early stopping mechanism, which prevented unnecessary training. Our CNN achieved a perfect validation accuracy of 100% as confirmed by the classification report and confusion matrix. The consistently high precision, recall, and F1 scores across all classes highlights the model's robustness. This technique not only enhanced training efficiency, but also ensured outstanding performance.
This section focuses on hyperparameter tuning and testing the CNN model to optimize its performance for lung cancer classification. Using Keras Tuner's hyperband, we systematically explored multiple configurations, including the number of filters in convolutional layers, dense layer units, dropout rates, and learning rates. The objective was to identify the best combination of parameters that maximized validation accuracy. The best hyperparameters identified, including a learning rate of 0.001, a dropout rate of 0.4, and smaller filter sizes in convolutional layers to reduce overfitting. The model was then trained with these optimized settings and achieved a high test accuracy of 98.6%. Validation loss and accuracy curves demonstrated smooth convergence, and the final model exhibited strong generalization. This approach highlights the effectiveness of hyperparameter tuning in enhancing model performance while minimizing training inefficiencies.
In this part of the project, we compare the traditional CNN model trained from scratch with a transfer learning approach using VGG16. Since VGG16 requires 3-channel RGB inputs, we adapt our grayscale CT scans accordingly. The baseline CNN, despite achieving moderate accuracy, struggled to generalize effectively due to the dataset size limitations. In construct, the transfer learning model with VGG16 leverage pre-trained ImageNet weights, allowing us to extract meaningful features without training the entire model from scratch. By fine-tuning only the classification layers, we achieved a high validation accuracy. The results highlight the advantage of using pre-trained embedding, which significantly enhanced model performance, particularly in cases with limited training data.
To further refine our transfer learning approach, we selectively unfroze the last 10 layers of the VGG16 architecture, enabling the model to adapt more precisely to our dataset while preserving learned features from ImageNet. This fine-tuning process was carefully controlled using a lower learning rate and early stopping to avoid overfitting. As a result, the fine-tuned model demonstrated substantial improvement, achieving a validation accuracy of 100%, as confirmed by the classification report and confusion matrix. Compared to the baseline CNN, it exhibited superior precision, recall, and F1 scores across all classes, reinforcing the effectiveness of transfer learning from optimizing performance in domain-specific tasks with constrained datasets.
This project successfully demonstrates the impact of deep learning and transfer learning in lung cancer classification using CT scans. By comparing a traditional CNN with a fine-tuned VGG16 model, we showed how leveraging pre-trained knowledge significantly improves accuracy and generalization, achieving a validation accuracy of 100%. These findings emphasize the potential of AI-driven medical imaging solutions in assisting early diagnosis and enhancing patient outcomes.